Hello and welcome to today's EMA Expo presentation from Dr. David Pommerenke. The topic today will be electrostatic discharge and its simulation. My name is John Twardock. I'll be your host for the session today. If you would like to submit any questions, please use the Teams webinar Q&A feature, which you can find the button at the top center of the menu bar, Q&A with a question mark. We would like to host questions throughout the session today. So if you have a question that comes up during the presentation, we'll be stopping at different points in the presentation to address them between the sections. So don't hesitate to get your questions into Q&A early, and then we will stop and address them as we progress through the presentation. So our speaker today is Dr. David Pommerenke, who is an IEEE fellow and also a world-renowned expert on ESD. He holds a PhD degree from the Technical University of Berlin and previously worked at both Hewlett-Packard and the Electromagnetic Compatibility Labs at Missouri University of Science and Technology. In 2020, he moved to Graz in Austria to join the Technical University of Graz, their EMC lab, and most of his research is devoted to system-level electrostatic discharge and EMC. He's authored and co-authored more than 150 journal papers and is an inventor on 13 patents. His research areas include EMC, ESD, electronics, numerical simulations, measurement methods, and instrumentation. So without further delay, I'll give the floor to Dr. Pommerenke.
Yeah, thank you very much, David Pommerenke. And I'm sitting here in my video studio. The background is actually a real screen. It's not an artificial screen. So I will have a couple short talks. In total, we have about an hour and 15 minutes. The first will be on basics of ESD. And I do think that's needed because many people will not be too familiar with some of the aspects of ESD. And then I just point at some challenges in simulations. I'm not showing some simulations which are directly obvious to do, but I'm showing where the frontiers are, where are the challenges, what cannot be done easily right now. So what we all need to work on. For basics, let me start with something very basic, which you may know from school. So on one side, we have conductors like metals, and the other side, we have insulators. So there's a broad range of impedances, from really conductors. And then there's anti-static materials in the middle. So materials, when they charge up, they easily discharge. But then there's really insulators, and of course on the top of insulation we have like polyethylene and Teflon. We know that triboelectric charging, so the contact between different materials, even between the same materials, causes charge separation. One side charges up, and so we get a voltage. And this voltages have pretty funny effect. One is, of course, if I take my tape roll and unspool it, I get voltage. So in display production or the peeling process is a problem. So in production, different layers are created from a display, and then there's a foil for protection. And when the foil is removed, a relatively high voltages occur. That's one source. But people also use it. There's electrostatic generators, where there's a water drop here, this is the water drop, and there's an electrical wire here, and there's a metallic surface here, and then they have hydrophilic different surfaces. I show in green and red, and when the drop moves down, every time when the drop changes from one material to the other, a voltage pulse is created. So the mechanical energy of the water droplet is converted to a voltage, and people have even turned on an LED doing these methods. Now, if we walk on a carpet, or things like that, then we have a metal object. This can also be a shoe, a foot. Here's the carpet, here's the floor. Let's say it's grounded. And there's charge separation here, and maybe minus on the floor. Once the foot goes up, of course, the negative charges stay. The positive charges stay on the body or on the metallic object. This is sort of the standard process from walking on a carpet. Now, in general, there's actually more negative charging of humans than positive charging, but the difference isn't that large. So both can occur. There's a slightly higher probability of negative charges. And now if there's a grounded surface here, let's say there's a grounded surface here, of course there can be a spark, as we all know. if we rub different materials with each other, usually one side becomes more positive, the other more negative. Most negative is Teflon. It's disputed if dry air does charging. I'll take it out. But you see the general tendency. For example, if you rub Teflon on nylon, you have a good chance that nylon will charge positive, Teflon negative. The problem is, this is the bulk material. In reality, everything depends on what happens on the surface. The surface, of course, is not smooth. These are practical surfaces. They have contamination, they have roughness, moisture sits on the surface. So the triboelectric series is just a general classification of what roughly to expect. And I say God created the materials, but the devil created the surfaces. And the surfaces are complicated. Nevertheless, the triboelectric series is a rough orientation of what to expect if two different materials are rubbed on each other, who charges positive and who charges negative. Let's say we are walking. So this is the walking side, and the voltages depend on the humidity, shoe floor, and details of the movement. And of course, we may have our negative charges here and positive charges here. Now, many things depend on how conductive the sole is, and there are a lot of nasty details to it. But alas, 8 can be reached rather easily, but it takes rare circumstances for 15 kV. Our lecture room is perfect. Our lecture room has really an old, I don't know how old, 30 years old nylon carpet, and it's perfect to make really large voltages. 15 kV is no problem, but it's rare. Most floors will probably not reach that. There are other situations where you can create high voltages. I will list a few. First thing is of walking. That's the first one here, and walking is a classical case. But sitting up from a chair, I'm sitting on a chair, and if I sit up, then of course my back rubs on the chair, and there will be a voltage. Then the worst is you go in skiing in a hut in winter, and you have a real nice oven. The air is super dry, and you take off your sweater. Then you can already hear it. And charge voltages for 20 kV, absolutely not a problem. Leaving an automobile also, you're sitting in the car, you rub on the backside, you're driving through Arizona in summer, it's really dry. Now, the capacitance is high because you're sitting in the car. But now you get out, and your capacitance is suddenly much less. But Q equals CV, so the total charge stays. Capacitance goes down, voltage goes up. And there are a couple other cases. The last one I mentioned is pulling a cable. You take a long cable, pull it along the floor, the cable will charge up, but it's very hard to get high voltages when you pull a cable. Now, Q equals CV, I already mentioned. So if you're in a typical US built structure, you may have only 70 picofarad to ground. But if you're in here, this is a stainless, this is not stainless steel, but this is reinforced concrete building. So my capacitance is maybe 120 pico. So for the same charge, I get only half the voltage. On the walking, there's a certain standardized test methods, the ANSI standard. And basically you see the blue person here, the blue pen person, and he walks like this step 1, 2, 3, 4, 5, 6. We call it the dance. While the person does that, the voltage is monitored. There are many ways to do it. Nevertheless, now, depending on the shoes, ESD, anti-ESD shoes, so slightly conductive, the carpets or the flooring can be slightly conductive to avoid ESD, or can be just household carpet. Different voltage will be measured, and there's a strong influence, of course, by humidity. Now, this is an example, not from walking, but this is an example from sitting up of a chair. So you see a couple thousand volt here, time, and the person has to sit up 10 times. And we see under these conditions, and the shoes are non-ESD shoes, under this condition with this chair and this clothes, we reach like 4,000 volt. Now, of course, in many environments, we do a lot of things to avoid ESD. So then there's ESD shoes, they are slightly conductive, and ESD flooring, which is slightly conductive. And same experiment, but here we see the voltage goes up only to 500 and quickly discharges. So the anti-ESD measures, or the ESD avoidance measures, like conductive flooring, shoes, of course, ground strap, all of these things are very, very successful. One can control voltage in production environment down to probably less than 50, 30 volts with enough effort. Oh, this is the worst case, not exactly shown as here, but you see more data. David takes off a sweater, drops the sweater. The moment I take off the sweater and hold it close to myself, I don't get a lot of voltage. But when I drop it, it goes really up, because the charge carriers on the cloth are put suddenly somewhere else. Now, we did a lot of tests on this together with Amazon, and here's the test data. This is by Michael Haney from lab A to Z. This is the Amazon research lab. 126 is A to Z. And we see voltages on the body and that humidity, and let's say 22 kV. And there are some relationships. Say we go from 50% somewhere here to 10%. The voltages go up maybe, let's say, 3x or something. They don't go up 100x, maybe 5x or something. So humidity is a dominating factor, and above maybe 60, 70%. ESD is very rare. It's very hard to make any high voltages. Here's another plot on humidity, somewhat showing the same. Most relevant is the top one. This is for very well controlled environment. The effect of humidity is much larger, but the start value is very low. The start value may be 10 volt. And now if you take all floors, all shoes, a wild mixture of everything you can buy, you again see maybe 3x, 5x. Typical effect of humidity on charge voltages in ESD. Now, of course, if the humidity is high, they don't even last that long, because the discharge rates are much higher. So dry conditions are the worst you can have for ESD. We need to talk about sparking. So the first thing we talk about charge processes. Now I'm going to talk about discharge process. And discharge processes can be modeled. Charge processes are extremely difficult to model because everything depends on the surface. Imagine we have a big ball and another big ball. We apply high voltage and we wait. And then we see at 10 kilovolt, we see about 2.8 millimeter. Or at 5 kilovolt, 1.1 millimeter spark length. This is Paschen's law. Paschen is long dead. His grandchildren are probably dead by now. But it's a basic law on electrostatic breakdown for homogeneous surfaces, and it's valid maybe up to, I don't know, 100 kV or something like that. Paschen's law. Now, in real objects, like a cell phone, here my cell phone, you may have a PCB here, and there's some plastic here, and the spark wants to go through the edge. Now, the edge is sharp, has sharp corners. It's not like big sears. So the spark will be across much larger distance. Maybe gun tip is not the right word here. We always call ESD simulators, we call them ESD guns. So what I mean is not actually a gun which can shoot bullets. I'm talking about the tip of an ESD generator. So I should have changed that word to an audience which is not so familiar with ESD. But interesting question, how long will the spark be? Well, this is a cell phone, a cheap cell phone. And look at that. This is all plastic. But here's a flex cable. And so there's a spark going this way. And I draw the spark separately. The spark goes here. This is the spark path. And it's about 5.1 millimeters and 7.5 kV is the breakdown voltage. This is very difficult to model still to predict using numerical tools, but EMA 3D is certainly working exactly on this question. Can we predict how long a spark will be? And not only in pure air, but the spark glides on plastic. Oh, and they love it. They love to glide on a surface, for example, on glass. So they can get much further than in air. But modeling of this surface to spark interaction is a difficult one, and you're going to see more of it. I want to look at something which is kind of important to understand why ESD simulation is complicated. So we have a ground, we have a metal plate, and the metal plate is ground. Okay. we have a charged person, and the person has a metal piece in its hand. And all the electrostatic energy from the capacitance around the hand, we can just put into this capacitor. And the electrostatic energy from the body itself, we put into this capacitor. And here we have time, and we are in time here. So we are prior to a discharge. So every solution now must be electrostatic solution. The voltage is high, and we're here in time. There's no current flowing. Now let's say there's a spark starts flowing, a current starts to flow. So current is here. Now we at the current. Typical current, maybe 10 amp. A voltage is collapsing, and here's the spark. And what happens now? We have a wave, electromagnetic wave, propagating outwards with a velocity of light. So after 1 nanosecond, it has reached 1 foot of distance. And the electromagnetic field strength is very, very high here. So we may have a change of the electromagnetic field strength of 10 kilovolt a meter in 1 nanosecond. Or we may have a magnetic field of 300 amps a meter, and it changes in 1 nanosecond. So very strong electromagnetic field. So in nanosecond earlier, every solution was electrostatic. Now we have antenna theory because we have very high field strength, and they love to couple into circuits and maybe crash the cell phone or give false impulses on my mouse. Now let's go further. Now we have 2 nanoseconds. The wave has reached 60 centimeters. Current is going down. Voltage is very close to 0 because there's a good spark there. Further, now things settle down. Change rates, the IDT, the VDT, the EDT all settle down. And now, of course, we don't have to use antenna theory anymore because everything is electrically small. Changes are slow. We can R. No, that was a C, R, L. We can use RLC models to model currents because we went into the domain where we can use circuits because everything is electrically small. So in a couple nanoseconds we go from electrostatic. First we start with tribal electrostatic physics, difficult one, charging. Then we have a static field. Then we go to antenna theory. We have the nanosecond pulses, and then we go back to circuit theory where we can easily model in any SPICE solver. Oh, we had that. Now, another thing which is important for ESD is if an object approaches, here's ground. Let's say at this distance the discharge is possible. It doesn't mean it will happen. The discharge can be delayed, so the object gets closer, and suddenly the spark happens. The reason is that spark couldn't start. Spark is like an avalanche, like in the mountains, the snow, and it takes a couple of skiers before the snow comes down. What it takes here, it takes initial electrons. Without initial electrons, the spark cannot be initiated. And thus we can talk about sources where they come from. But nonetheless, what happens, the field strength is here. This is electrostatic field strength. The discharge becomes possible here, but it happens here. So the field strength is higher when it happens, and that makes the ionization much faster. So the rise time of the pulse may, instead of being 2 nanoseconds, only 50 picoseconds. And that makes much higher the IDT. It couples into every other thinkable circuit. So the time lag is usually long in dry air, and that dry air, we not only have more charges, but they last longer, and the discharge is worse, dry air. Just an example here, this would be a discharge of, I think, 8 kV. In dry air, we may get 100 picosecond rise time, and in moist air, we get like 2 nanosecond rise time. And that's a 20x change in the current derivative, 20x change in the RF content. Humidity is important. Another look at a similar thing. This is mainly discharges. Every cross here is one discharge. Peak current, and this is the length of the spark, and we see a 10 kV, 2.8 millimeter. That's Paschen length. We get 20 amp. But if the spark is shorter, wow, we get 140 amp for the same voltage. So when we model spark breakdown in the tools, EMA 3D, then the fact that the shortened spark leads to much faster ionization needs to be taken into account to correctly model ESD. Oh, let me just summarize this part, the first part. First, we have charging. We have to model. We think about tribal electricity. It's really difficult to model because surfaces get in contact. Surfaces, are separated again, and real surfaces have dirt on, water, everything. Next modeling scheme would be fields, electrostatics. That's easy. Then the spark comes. Sparking, we have to model plasma physics. Plasma can be a soft plasma like in space around a spacecraft, or it can be a highly ionized plasma like in welding, arc welding. The more it's ionized, the more difficult is modeling. The plasma causes a current change. That everything has to be modeled. Antenna theory, I think linear antenna theory like metal and air is relatively easy. This couples into the circuit. Modeling depends on the complexity of the circuit. The circuit has a response. For example, the phone may crash. But then to model that, we need to models for the soft failure, so for the crash sensitivity of the ICs. Those can be created, but it's tough. And then damage to circuit, semiconductor physics. If the current is too high, for example, there may be local melting in a PN junction, or if the voltage is too high, the gate oxide may fail. Nevertheless, in summary, many different aspects need to be considered in the different moments from tribal charging to semiconductor damage, and that covers a broad range of simulation, and many of these simulations are then multiphysics simulation. Yeah, this is the first part here, and I think it's time to ask for questions.
Well, we have a question, David.
Yes.
We have a question with regard to time lag, discharge initiation, and current rise time.
Yeah.
Is the faster current rise time solely due to the gap being overvolted, or is it due to the relatively shorter arc length, all things being equal?
Both. You can't, the gap is overvoltage because the arc length is shorter. So you can't separate both. So the gap is, you can only overvoltage a gap by making the gap shorter or the voltage higher. So you can't separate both effects. That would be my answer. Or I misunderstand the question.
Okay, I don't see any other questions at this point.
Yeah, the person can make a follow-up question, yeah?
Yes.
No problem. We can, now I want to go to a relatively complex situation of ESD modeling. And if this is something, we are working on, think about, we have a cell phone, and this cell phone has maybe 10 antennas at different spots. And then it may transmit at 800 megahertz, but at the same time receive at maybe 2.4 gigahertz. So the 800 megahertz transmitter cannot have harmonics. Harmonics have to be really suppressed. I'm talking about 130 dB suppression of harmonics. Otherwise, my 800 megahertz transmitter would just destroy the sensitivity of my 1400 megahertz receiver. So we have problems of harmonics. The next is ESD. If I discharge to the antenna, then the antenna should survive. The antenna, the metal part, will survive anyway. But the associated, for example, antenna tuner, aperture tuner, LNA, low noise amplifier, or power amplifier, they all need to survive the ESD. And these antennas are often not even connected to the body of the phone, because each antenna may have multiple coax connections and no, let's say, ground connection. So we have ESD, we have to protect against ESD, we have to avoid harmonics. And one problem is the ESD protection devices like the transient voltage suppressor, TVS diodes, they are PN junction, they cause harmonics. So the overall challenge is to make a co-design in simulation which contains ESD and harmonics. Look at the typical antenna design here. Let me turn on my pen again. I hope the pen is not confusing. So we have the antenna here, and the antenna may be connected to the body of the phone or not. Here is a power amplifier or LNA. Usually there's an antenna tuner here with switches, and Antenna tuners, for example, there, if I change frequency or if I have the phone close to my head, the antenna detunes. So the antenna tuner tunes us back. And there may be an aperture tuner at the end. Here's another tuner. And this tuner can, for example, change something about radiation direction, can do a bunch of other changes. So, and each of the switches is a CMOS switch. They are silicon on insulator switches, and they are relatively robust, but if a strong ESD hits, and the ESD doesn't find a current path to ground. Ground means the body of the phone. It's not really ground. Real ground is for the potatoes. But then the tuners can be damaged. So everybody would be happy if we can put like a TVS diode here to local ground. But the problem is the TVS diode causes harmonics. Now there are many ways how the antenna can be connected to the body of the phone. Nice if it's connected directly. Sometimes there's an inductor, and if the inductor is small, like below 10 nanohenry, it's actually quite a good ground connection. Or one can have an inductor and a capacitor, even better. Whoop, some current flows to ground, and if the capacitor is like 1 picofarad, then lots of RF content will not make it to the LNA. This looks similar, but the capacitor may spark. Not good. And there's combinations, L, C, TVS, etc., etc. And capacitors will spark. If you take an SMT capacitor, let's say you take a, I don't know, 10 picofarad, and the thing is size 0201, and you apply like 500 volt or something, it will spark. And if you're lucky, it sparks on the outside. If you're unlucky, it sparks on the inside. If it sparks on the inside, it will break, it will crack. So the problem is also if it sparks, the current bang quickly goes up because these are very ugly discharges on the surface. The spark may only have rise times of 50 picosecond. So this is some of the challenges which is done from the ESD side for the phone protection. Now harmonics. Let's say we have a carrier here, and the carrier is, what's the typical value? 30 dBm, like 1 watt on the phone. Yeah. But the sensitivity at maybe 2.4 gigahertz, maybe 1 is 125 dBm. So we see 150 dB difference. 150 dB is a lot. So even weakly harmonic structures are ugly. And there are basically 2 types of weakly harmonic structures. One is the TVS diodes. The other is contacts. Metal contacts make harmonics. So if you have an excellent contact with a lot of pressure and gold surface, they don't make harmonics. But in reality, on the phone, if you have a little clip which connects, the, let's say, the stainless steel backside of the display to the, let's say, body, oh, they cannot make a lot of pressure. Stainless steel has oxide layers, etc. These contacts make harmonics, and they can make pretty ugly harmonics. Maybe at 30 dBm forward, they can make minus 40 dBm, so only 70 dB distance. 70 dB distance would be really bad. It would completely destroy the sensitivity of the receiver. Now what can we do for protection? Now we can put our antenna here. This is the antenna. And maybe here's the feed. And maybe we are lucky. Let's say we can put the TVS here, or we can put it here. This is not a voltage source. This is a transient voltage protector. And if it makes harmonics here, they may not be radiated because at this feed point, the antenna doesn't have a good impedance or radiation impedance for the third harmonic. So what we want to do, we want to make a co-optimization. To one extent, we need to make the ESD robust. On the other side, we have to avoid harmonics. So the question is it possible to find a location for a TVS diode and the right type of TVS diode such that we get ESD protection, but the harmonics caused by the TVS, they cannot be radiated because the antenna doesn't like to radiate if excited at that frequency, at that location. Sort of the co-optimization questions, which is, by the way, not solved yet. Well, here's an example of simulation. We all know there are multiple simulation tools. This is a Samsung phone. This is a reverse engineered antenna. And we have the RF source here, and there's lots of RF switches, C, L, C, all kinds of networks in between. And now what we look at is the voltage at the antenna, because the voltage antennas can be very high, These are probes, and if the voltage is very high, then the TVS diode is not allowed to turn on. And the higher the voltage, the more harmonics it will make. So voltages you'll see are high, so TVS diodes have to be made sure that they don't cause any harmonics in the wanted voltage range, but still protect ESD. And now one simulates this antenna simulation. It's relatively easy if the geometry is understood. And we see there's a tuner that tunes inductance. For example, the inductance can be 68 or 29 or 19 or 12 nanohenry. And we see the resonance frequency moves. And this is a typical antenna tuner. It has multiple inductors. It switches between the inductors. It's not a tunable inductor. It just switches. And this way, the antenna resonance frequency can be tuned to the frequency of interest. Now, if we look at that, what happens to the voltage at the antenna? And I take this end of the antenna, and this is the aperture tuner inductance. And this is a combined model with geometry. What we see in voltages, we see up to 80 volt here. And that's quite a bit, also for ESD protection devices. So if we would place the TVS diode at this end, it may not radiate well at the third harmonic, but the harmonics created by the TVS diode may be very high. Now, if we place it at this end, the voltages are much lower, but the antenna may radiate harmonics very well. So it's an interesting trade-off where we need models for the harmonic creation of TVS diodes. Those are not easy to make. We need models for the ESD protection of the TVS diodes. Those are relatively easy to make. And then we need, of course, a relatively good, precise antenna model with all the feed and aperture tuners. And so that's where the challenge lies. The challenge lies in making all these combined simulations, which include weakly harmonic effects. Yeah, that's basically this section, the section on antenna design or antenna front-end design, and it's a complex co-simulation. What we're working on, and I think all the cell phone manufacturers, their challenge, they see the same challenge and have the hope for the same solution paths. Any question?
We had a second question. I believe it was what are the key factors in the arc rise time?
The key factors in the arc models itself for the first 10 nanoseconds, they basically, Rumper-Weitzel model basically says something like the resistance, that doesn't write, what's going on? The resistance of time, the resistance of time of the arc is something like some constant, and then we have integral I squared. So basically, this is the arc resistance over time. And I squared means the current which has flown in the past, whatever nanosecond, determines the resistance now. There are some constants here. Yeah. So it means basically every charge carrier which flows through the arc causes new charge carriers, so reduces the resistance. And this is modeled from Rumper-Weitzel. It predicts for the first 10 nanosecond quite well for ESD with EMC accuracy. EMC accuracy is not highly precise. That's a Rumper-Weitzel's model. So one of the factors which is included in K is the length of the spark. So if the spark is shorter, there will be more current flowing. If the more current is flowing, the quicker the arc resistance goes down. And let's say at 5 kV with 1.1 millimeter arc length, it will take about 2 nanoseconds before like an arc resistance of maybe 20 ohm is reached. If the spark is shorter, let's say 0.3, then it will take maybe, I don't know, 100 picosecond to reach this value. I hope I helped to answer that question.
Do we have any other questions? So again, post them with the Q&A button, which is the top center.
Okay. We go to another aspect. This is another rather difficult simulation problem. Let's say I take my phone here, that's my phone, and I put the phone on the table, and I come charged, and I touch the phone, the glass, because I want to find out what time it is. Now I will not feel a spark. I will not feel a spark, but there is quite activity going on. So what happens is, here you see the finger. The finger, there's a discharge, but it doesn't cause a spark. But the current can be 10 amps or 20 amps, can let's say be 10 amps, the current. And the current spreads on the surface. And you see it spreads on the surface, and typical diameter of the structure is like 30 millimeter. So the current cannot go through the glass. The glass is a super good insulator. But the current can spread on the surface and changes the top potential quickly. And then there's displaced current flowing. There's a displaced current flowing through the glass, and it may flow into some patch from a current sensing circuit for touchscreen, or it may flow into the electronics. And the things you see here, these are actually patches on a PCB, which we do to compare simulation and measurement. And this is the sparkless discharge. And it's a significant problem for each display technology, because the currents are high and all the currents flow as displacement current into the underlying structure. So how do we get that nice picture? Oh, that's quite simple. We take the phone, discharge on it, and after the discharge, the charge carriers stick on the surface. So they stay there for minutes, especially in dry atmosphere. Then we take a toner from a laser, break it open, and we blow the toner on it from the laser toner. Now the toner is of course electrostatically activated, so the toner will sit on the charge carriers on the glass, and then we get these nice figures. These figures are called dust figures because dust is used to visualize them. Their new invention, the first publication is from 1776. I'm not joking. First publication is from 1776, and at that time they used lead sulfide as a material to visualize. We don't use that anymore for some reason, but we use toner to visualize that. Now this is a tough one to model. You have all the spreading, of the arms, and you have a surface discharge gliding on the surface, and there we are working on some modeling of that. So here again you see the dust figure. You see one path. This is a path of one streamer. These are all streamers. And roughly speaking, here's the electrode, and there are more charges here and there are less charges here. And there's a voltage drop along the streamer, and one can estimate that it's maybe 500 to 1000 volt a millimeter is the drop. So the voltage here at the end is so low that the streamer can't grow anymore. And the voltage here will be roughly equal to the ESD voltage. Now, how do we model that? There are many approaches, but one is we break the streamer into segments, many segments, and for each segment we use a Romper-Weizels equation. And I said the resistance, and then integral I squared, and some constant. And of course there's a capacitance through the glass. The glass of a phone is thin, so we have capacitance which charges up, capacitance, and what's called return plane. That can be the touch circuit, or this can be the actual display. So we get a nonlinear R capacitance, nonlinear capacitance, nonlinear capacitance, and we get a systematic voltage drop along the streamer. So this leads to more complex models. In the end, there are models, resistor. This is one streamer, another streamer. One can make many streamers. 30 is a good number. And this gives an nonlinear capacitance coupling to the display, nonlinear capacitance coupling to the display, etc., etc. But if the nonlinearity is not really taken well into account, one cannot model, broad range of cases. One has to adapt parameters for each case, which is ugly. Here are advanced models. This is done on soda lime 2 millimeter glass, so rather thick glass. Here you see the dust figure, 9 kV, 12, 15 kV. roughly similar diameter, not a large change, and you see simulation of model, and we see like 10 amps of current and a little bit more than 10 amps of current. But this is all done on a SPICE basis. This is not on a charge carrier base, and that's the pity of it. So the pity of it is in SPICE, you know, let's just say SPICE. SPICE does not distinguish between electrons which move or positive ions. But in reality, the dust figure is totally different for positive or negative. So for positive discharges, we get all these nice branches. Yeah. But for negative, we just get one big bob. So that already indicates that modeling based on SPICE, where current is current, SPICE doesn't care if it's positive or negative, charge carriers is in principle fundamentally wrong. So EMA 3D is working on this FTDT-derived particles, charge carriers in cell modeling, where really the charge carriers are taken into account. So to be much more physical than to be have a much more physics-based result than this model where we press this into a SPICE simulation. This is this part. Any question?
I see no new questions. I see one. I'm sorry. Why is the apparent arc length longer along dielectric surfaces versus through air directly for the same voltage?
No, that's very easy to explain. The reason is this is very old theory called Gleitentladung, all from 1800. Think about, we have ground here. We have a thin insulator here. Thin. Yeah. And now what the spark does, the spark grows here. Yeah. Now the spark charges up this capacitance. Then it grows. Charges up this capacitance. And because it charges up capacitance, there's more current. And if there's more current, this resistance in this section goes down. And the potential in this point, because there's less resistance, goes up. Potential, let's say, V. Yeah. So the spark has a lot more voltage here to grow the next segment, and then it charges up the next capacitor, So the thinner the glass is, the higher the dielectric constant, the more the spark can carry. Let's say here's a ESD gun, 10 kV, can carry the potential to here, to here, to here, to here. So the spark can carry the potential much further because it had so many nice capacitors it could charge up. And every time to charge up the capacitor, it needs to push charge carriers, and charge carriers make new charge carriers. So on a thin, high dielectric constant, the spark can grow much, much, much further than in air.
And a follow-on question, is that explanation true for even when the dielectric is not close to a ground plane?
Oh, yeah. Now, next question, please. Now it gets more difficult. We know that on dielectric surfaces without ground plane, the spark develops faster. Some of these constants are even a factor 4 higher. We don't know exactly why the spark loves to go and grow faster on a dielectric surface which is not backed up by a ground. We don't know the reason.
That's fair enough. Okay, I don't see any other questions yet, but again, feel free to submit as we go.
Okay, now I will go to heterogeneous integration. Now, this is kind of what comes up in the future on IC design, and now we look at a more modern IC here, and this is heterogeneous integration, so different technologies are integrated. For example, we have all kinds of DRAM, we have logic IC, we have a physical layer interface, we may even have an antenna, etc., etc. So here we have an I/O, and we may have a TVS, so we may have a board level protection, and then the energy may flow here, the ESD, and then there's maybe the physical layer interface chip may not have another level of protection. So we have this protection, and then the current may flow. There's another phi shown here, go in the logic die and go into the memory. And the memory may have, because it has a lot of IOs. Now IOs reach 100, but now IO will reach 10 to the 7 per square millimeter. Many IOs. So the pitch between the IOs may only be 1 micrometer. 1 micrometer. This is not an IO to PCB, but it's an IO which is from one die to the next die to the next die. Now, the ESD robustness may only be 5 volt. So meaning the most critical process in production, if let's say this is a small IC, we call this chiplet, and it's mounted on another chiplet. So there may be a voltage from handling between. So there's a micro, I don't want to call it spark, a micro discharge. It's called charge device model. So the one chip is charged and then it touches the other. And the current flows only for 100 picosecond, 200 picosecond, and may reach, depending on the size of the IC, amps, but for the small ICs only milliamps, but milliamps is a problem already. So the new ICs, they have maybe an ESD robustness of 5 volt now. It previous was like 500, 250 volt. In production, that means all voltage, all the static control needs to be super good. This is the challenge in heterogeneous integration. And to handle that, one may need, for some I/O, let's say USB, one may need TVS on PCB, one may need another protection level here and another protection level here. Now the risk is that the weak protection protects the strong protection, so this now needs to be simulated. It needs geometrical models because we have wave propagation. It needs so full wave models. It needs then maybe SPICE models for the TVS, different TVS, and this all needs to be combined to a relatively complex simulation. Now for ESD design, damage can occur by current and by voltage. Voltage is gate oxide failure, current is usually thermal failure. Now the normal IC operating range soon is maybe the voltage VDD may be only 0.7 volt. And the current may only be 1 milliamp, maybe less. So this is the operating range. And if the current goes too high, IC dies thermally. If the voltage goes too high, gate oxide failure. So basically the design window is shrinking because this boundary moves down, this boundary moves here. So it turns out that lots of these designs, especially if they're multiple protection devices work together, cannot be done by intuition or datasheet anymore. They need simulation. I look at charged device model. This is the IC idea. Here's the IC. It's charged. The IC has a capacitance to ground. And then when it touches, there's, let's say, a micro spark here. And this is not tested like this because its reproducibility is bad. Tested, it's you put the IC here, you charge up the IC and you ground it here with using a micro spark. But micro spark doesn't work well below 100 volt. So there are alternative methods being developed. But for a relatively large IC, you may 6 amp of current and the pulse is 300 picosecond wide. Now, current needs to be measured, and the measurement is not always trivial. The classical method, you take a disc resistor. This is a disc resistor. There is resistive material here. It's maybe outside is like 3 millimeters. And then there's a resistance from here to the outside of maybe 1 ohm. And then this works up to 10 gigahertz or something, but not above. Now we need to be much above because this micro sparking has super short rise times. And now the method we designed is here's like the center where the ESD would go to. And let's say we attach 1 trace, 50 ohm trace, then the impedance is 50 ohm. But if we attach 2, it's 25. And if we attach 3, blah, blah, blah. So we attach 16, so we have 3.12 ohm impedance, and this is all full wave simulated. So we can get a good 30 gigahertz or more bandwidth out of such a target, ESD measurement target. When measurements are done, the different size objects, small, larger one. The object is mounted here, and then the motors bring it down in a defined fashion. And the micro spark is here, and this goes to a fast scope. And here are some results for different sizes. Here's a small size, larger size, but we see maybe, I don't know, this is at 30 volt. So we see 0.5 amp, but this pulse is rather narrow. Larger object, wider pulse, pretty obvious. Well, if you make some histograms of that, we see that here's a rise time, object size, and 10 volts, 30 volts. We see that rise times are down to 15 picoseconds. And 15 picoseconds, oh, it says, it's not easy to measure with our instrumentation, which we have. It's we can measure 50, we have 50 gigahertz bandwidth scope as the fastest which we have. But the problem is, of course, add a meter of cable and the bandwidth is lost. So the challenges for future things in simulation is, number one, try to model the micro sparking at 10 volt. Number two, the inside an IC at 10 picosecond rise time, even the small traces inside the IC are not just metal blocks. Wave propagation needs to be modeled inside von ICs. And to combine that with nonlinear models of the maybe sparking and maybe nonlinear models inside the IC of gate oxide damage or of metallization damage. That's where the challenge lies. Now, to test, we make pulse generators. So we try to make pulse generators with less than 20 picosecond rise time. And our goal is 500 volt with less than 20 picosecond rise time. And we follow different concepts, optical concepts, liquid metal concepts, some partially mercury, partially other liquid metals. And this is just a measurement of one of our more successful experiments. So we get about 20 picosecond rise time, and we have like 200 volt or something here. But it's an ongoing challenge, not only to make the pulses on Monday morning where they work well, but to make a reliable test system, which is quite not the same. Universities are good for prototypes. They're not good for any commercial products. Yes, another thing, we need to make antennas. This is an antenna, and we hope to make the antenna from 0.5 to more than 40 gigahertz broadband antenna. And the goal is that this antenna, if there's an ESD in a production, we want to put we cannot measure the current in the production. It's impossible to get there. But we can place a few antennas, and then we can get the signal, and from the single spectral content, we can back calculate what the ESD was. And now to do that, the antennas have to have a clean time domain response. In simulation, it's easy. But here, this is simulation model. We see directivity. I think every solver can do that. It radiates in this direction. And we see at 40 gigahertz, the gain is higher than at low frequency, which is obvious. But the beam is not spread in many directions. At 40 gigahertz, we still have more or less one beam, one quite okay beam. Now that doesn't work in practice so well, so we have to change the feed structure. Yeah, that's this part on heterogeneous integration. I tried to get a little outlook of what comes in ESD for future products and what consequences this has for modeling. Any question?
What technology do you think is going to be most disruptive, maybe in the next 5 years, David, that will affect this field?
Do you mean what application or what technology? I mean, this will stay in CMOS. CMOS has been called dead many times, but CMOS has always developed further. I mean, of course, there are always applications for gallium nitride, for power electronics, or silicon carbide for power electronics. But there's graphene transistors, there's many other sort of technologies which are available, but they're all not yet at a large commercial stage. So far, CMOS has beaten every expectations, and there always have been niche like gallium, germanium silicon, gallium arsenide, indium phosphide, graphene, a couple of other technologies, but they have not really hit the mainstream except for special products. And so I think CMOS will still be there in 10 years. And for the applications, of course, if I take a cell phone, now the cell phone may have radar at 20 gigahertz. It may have Schottky diode detectors for other things. They are very sensitive Schottky diodes. Easy to destroy. So the frequencies goes up in 5G, 6G, whatever, 7G, and the addition from RF sensing, radar, etc., will cause include more RF devices above 10 gigahertz. And of course, the faster the device, the more easy it is to damage.
We have one question. Yeah, we have one question kind of along these lines. Do you need multiple antennas and a time of arrival approach for fully implementing the ESD antenna idea? Or is the location of the ESD well known enough to not need more sophisticated techniques?
Well, in most cases, let's say there's a placement machine and there's something happening here. One knows pretty well the location. I mean, has a very good guess on the location. Location is here. But if you wanted to quantify the problem, I mean, then the problem is that the machines are very complex. So waves do everything what they like to do. They bounce off. So we can't do clear time of arrival. So we place an antenna here and antenna here and antenna here. The classical time of arrival will not work because it's wild amount of reflections. And so what we mainly care for is what type of ESD is. Was it like a CDM or a human operator or just a discharge on the surface? And that we can mainly do by spectral information. So if this is the frequency, each type of ESD will have its own spectral signature. That's a core element. Then we want to know how large is the current. Of course, how large was the ESD current, but of course the spectral content is linear to the amount of current flowing, or actually is linear to the derivative of the current. So spectral content and magnitude are basically the main things. Location is usually known. We also have video recording, acoustic recording, so we use other ears. And one needs multiple antennas because we don't know which direction it goes and we don't know which polarization it will have. I hope it answers it.
Yeah, I am curious about your comments on where education will go in this space as well. We are noticing that most undergraduate programs do not really teach much in the way of EMC or ESD, certainly on the electrical engineering side. Do you see that changing in the future, or what do you see bridging the gap between where physics is and electrical engineering is?
Well, I mean, there are some universities in the world who do this. We have more than 50 students in our EMC lecture and labs. We have the largest EMC program if it comes to attendance in Europe. And but many universities don't do that, and so students can select what they're interested in. And I think some of these things are not bachelor level, they are master level. And we try to promote it, and we have a lot of activity on making videos and teaching material online. For, the smallest is just watch a video. The next is maybe their learning objective and self-assessment. And some videos. The next is maybe there's learning objective, and then there's group work online with the faculty and maybe an exam. Or next level up is the same, but there's on-site training, so people come here and do experiments, and we call this a module. And multiple modules can be combined to make a course or a class, and multiple classes can be combined to make like a master thesis, a remote master thesis. We offer this, and this is a large portion of our institute works on developing well-structured online learning material on electronics, EMC, ESD, starting from just watching a video. Everything is for free, but going up the hierarchy to making a remote master.
Well, thank you. There certainly we are seeing a rise in the need for the education.
Yeah, we just did a questionnaire to industry, asked what they're interested in. It's quite interesting. Many of the industries, these are small companies, they are mainly interested in EMC PCB design. Although I think how to do this well is actually known, but they simply don't know how to do it. So there's a lot of knowledge transfer from the companies like the Apple or Huawei or Samsung, who really know what they're doing, to smaller companies. And of course, the big companies, they have this rule checkers, and they're highly sophisticated rule checkers. Apple has multiple people with PhD just to update the rule checkers. And they are very good on PCB design. But many smaller companies have nothing, and they make many mistakes like multiple ground planes and, the usual things you should avoid. So, but there's a need for education. And there, if you go to the web, there are quite a few, let's say consultant who do a good job. Todd Hubing, and a couple of others who do a good job. There's a lot of kind of nonsense, but still, well, many competent people in the field. Any other question?
Well, I don't see any questions posted, so.
Then I go to the last part. Yep.
Okay.
Last section. This is what we do with EMA 3D, and Charge Plus, simulation and verification. So there's a big interest in modeling plasma from low density plasma to really sparking plasma. And many of the tools are, there are two competitors, I think, mainly in the world who do that. And I think they are better on low density plasma than on the transition to sparking. So what we do is we make test setups, we measure spark resistance over time, compare that to simulation. And here's a setup shown before you look at the video. Here's a setup, there's a rod here, this is the rod. And the rod is charged. And then there's a spark here, and it discharges into a ESD current target. And if you look at the video a couple of times, you see the spark hitting, going to the electrode is approaching, is moving, and then there's a spark going to an ESD current target. It's not easy to see, but with a little fantasy, I think you can all do it. Now, in the setup, we have this discharge tube, and this discharge tube is a transmission line, so we can model it LC, but we can also model it full wave. It's a transmission line, and let's say if the transmission line would be constant, and you discharge it, here's time, it's like 4 meters, oh, something has happened here, then theoretically you would get a perfect square wave if the spark is just an ideal switch. Now there are some effects on the front, there are some extra capacitance here because this wall is vertical, so we get a little peak. But in general, what we get is a curve. Let me find this empty space. In general, what we get is a curve. Hey, I can't write. I need to motivate my computer to let me write. Okay, what we get in general is, let's say, an ideal square current. This is I, and this is T. If the spark resistance is, let's say, going from infinite to 0, but in reality, the spark resistance has a transition from here to here. So from the difference here, we can calculate the actual spark resistance of time. We can calculate R of time. And there's a, yeah, and then we can calculate aspects like the current derivative. So of course, if the current goes up like that, the derivative is infinite. But if the current goes up like that, the derivative is its value. And this is shown maximum the IDT measurements, 5 kV, spark length, and the 1.1 millimeter is Paschen. That's the longest, which is kind of possible without nasty stuff. But if the spark length gets shorter, the derivative goes up, and here we have here we have maybe 1,000 amps a nanosecond. That's quite a severe rising edge, which can induce a lot of voltage. Now this is all compared to the simulation. This is the simulation model. This is the rod, ground, ESD current target. Here's a target, and the sparking. So there's areas where ionization is allowed. And one sees that measurement and simulation for some cases works excellently in this modeling. For some cases, we're not fully there, but it's getting there. So the spark modeling is getting there, but it's not fully there. But the tools can visualize things the eye cannot do. And here's an example. This is the air conductivity. So how many charge carriers we have per cubic meter. And the front end of the structure looks like that. So it's not really rounded, but it has, and the other side looks like that. So we have a very large electric field here and at the edges. And that's what we see in the density. So here's the round, and here's the center. So we see, and here you can see it from the side. So we have edge effects and center effects. on the charge conductivity. Now, we look at the air conductivity and other parameters, trying to optimize the equations which cause the discharge and which cause the ionization to match measurements as good as we can. That's basically it for this talk. And so I'm happy. Hope you learned something, and I'll take a further question.
Well, thank you, David. I don't see any further questions, but I've been watching and following the project that we're working together on, and I just thank you for the work and the progress. Sue's doing a fantastic job with your also with your math.
We have to praise Xu Yang.
Yes. One question. Can you qualify your remark about EMA 3D being good at small arc lengths?
Yeah, that's it gets deep into it. The point is, the model it's if the arc sparkling, let's say we take 10 kV. And we take a model, we take 3 millimeters distance. In theory, there would not be spark possible because it's more than 2.7. In homogeneous surface, it wouldn't be possible. But what the tool does, it starts to do ionization. And in reality, we have processes which cause ionization, but we also have processes which cause recombination. And streamers which start to fly, they can die because simply they don't have enough field strength to cause enough ionization. So there are processes which kind of terminate sparking. But I think there the implementation isn't really fully yet there. So there could be a spark created over a distance where it's physically not possible. But in the tool, the spark is simply delayed very long. So some of the, let's say, processes which reduce the temperature, channel expansion is one of them, recombination is another one. They are not fully modeled in the equation to the point that sparking cannot happen over distances where or the simulation may show sparking where sparking cannot happen because this recombination or the quenching effects are not modeled very well. And then in reality, for some other situations, the spark resistance, if there's a spark, will always go down very low. Give it 10 ohm, 20 ohm if there's enough current. In the tool, sometimes the spark resistance doesn't go fully down, which may not be so bad for making many predictive simulations. It's still, but it's still there that there some of the processes which cause ionization may not be fully implemented correctly yet in some of the quenching. But overall, I mean, if somebody would have told me that this can be simulated 5 years ago, I would say impossible. But now there's a lot of progress of what can be done. And honestly, EMA 3D's tool 3 years ago were by far not at the competence level they are now.
Well, a follow-on question. What range do you consider to be a small arc length, and what are the limitations you see for longer ones?
Okay, I use passion length as 100% value, so 2.7 millimeter at 10 kV. And a small value is 30%. Extremely small value is 30% of passion. So 1 millimeter at 10 kV is a pretty small value. It's hard to realize in practical experiments. Same for 5 kV. 1.1 millimeter is passion. 0.3 millimeter is very hard to realize. It needs super smooth surfaces and very dry conditions. So that would be a very short one. So the range passion to 30% of passion. So the range we look at in most cases.
And a follow-up question. Is there anything that a user or we can look out for in the model that would help us to tell us when a modeled arc is actually not physically possible? Any hints there?
A few PhDs would help, and reading, all the classical books on spark discharge. Let's say we talk about sparking under normal pressure in air. Then the spark length is an indicator. If there's sharp surfaces or they glide on surfaces, then spark length can be longer than Paschen. If there's a spark in more or less homogeneous field longer than Paschen, then I think this would not be right. I think these are the main things which are easy if you don't have some level of experimental data or some level of experimental experience.
Are there references that you would recommend on spark discharges and electrical breakdown, ESD? Any references that you would recommend to the audience?
I'm of course an arrogant professor, so I'd recommend, of course, my own publication. Yeah. But there's the classical books, but the books are not easy to read. There's a book from Reiser, R-A-I-Z-E-R, Yuri Reiser. It's maybe from the 1980s. It's called Spark Discharge. Yuri Reiser. That's one of the classical references. Then there's lots of people who worked on sparking mesyats, M-E-S-Y-A-T-S, mesyats, classical high voltage pulse guy. Then there's Meeks and Craggs, also very old book. Meeks, M-E-E-K, Craggs is C-R-A-G-G-S, Meeks and Craggs. They have this big black book also from 1970s. These are old books. But these people have done pretty much everything experimental, and they have given a lot of useful basic theory on high voltage sparking. The only problem is if you read them in a bathtub, you will dissolve before you even reach the midway point. And so they are kind of extensive books of what they did all their life. Mesyats, Meeks and Craggs, and Yuri Reiser. But still, they are although they are old, they are kind of references in the classical high voltage discharge books. Then there's what else? The dissertation from Colorado School of Mines, isn't it? Colorado School of Mines. They work on spark modeling. There's a dissertation. What's his name? Do you remember the name? But you can check spark modeling or ESD on. And your Colorado School of Mines, and they not do it for electronics, they do it for explosives, so that the dynamite which they use for mining doesn't accidentally blow up because of ESD. So they have another interest. So they may not model the first 10 nanoseconds well. They want to model larger time frames where the energy transfer to the dynamite is large enough to blow it up. But they are also, I think they are quite competent. Colorado School of Mines, there's a dissertation. What else? For ESD system level, I think I did quite a good publications. There are Fujiwara in Japan. I think also Ken Kawamata, but that's the same group, Fujiwara, Ken Kawamata. It's the same group. Of course, Missouri Roller, a couple of PhD students who worked on that or who used this. I think that's my shortlist. People can email me. Maybe, yeah.
Very good.
Maybe I should put my email somewhere.
Yes.
Did I do it? Yeah.
Bring up a blank slide and type it very large on the slide. There you go. All right. Do we have any further questions? I thank the audience for their participation today. And David, thank you for a very extensive presentation. And as a reminder to everyone, if there are unanswered questions or if you would like to follow up, you can certainly do that by email to EMA. Those of you who have attended, you will also receive an email from us with a link to a recording of this session. So if there's something you wanted to go back and review or share with your colleagues, you can do that as well. Our next actual keynote event for Expo will be tomorrow, July 2nd at 11 a.m. Eastern Time. This one will focus on kind of an emerging topic where Dr. René Fugger from CADFEM will share advances he has made in applying universal machine learning to electromagnetics. So I hope to see many of you return for that presentation as well. Again, David, thank you very much for your preparation and your presentation today. We appreciate your time. Attendees, thank you for attending. And I will close the session.
I learned a lot about when preparing, and I learned that I could use our own video studio. This is where we make the educational videos to present, which works, I think, actually quite well from a camera perspective. I hope it did.
It did very well. Your shots on camera look very good.
Yeah, better than me. It's a beauty filter. That's why my laptop ran out of power.
Well, thanks everyone. I will close the session out now. I appreciate everyone's time. Bye now.